So thanks everyone for joining. This is the second IGS seminar series of the year, the first focused on sea ice. I hope everyone had a good holiday break and 2024 is off to a good start. This week we only have one presenter. We have Damien Ringeisen, who is a postdoc at NASA Goddard in New York. And Damien is going to be presenting some of the work that I believe carried over from his PhD and postdoc and into his current position on the linear kinematic features of intersection angles in sea ice. And yeah, I'll pass it over to Damien. And just like usual, please save your questions in the chat or save them for afterwards. And because we don't have a second speaker today, we do have a nice chunk of time at the end for questions and discussion. So hopefully we can have a nice chat after the presentation. And with that, I'll pass it over to Damien.
Yeah, thanks a lot, Dave, for the kind introduction. So yeah, thanks a lot for having me also in the seminar. As Dave said, this is work that I started during my PhD at Avi with Martin Losch in a collaboration through ArcTrain with McGill University with Bruno, with whom I went to do a postdoc. And now I work for NASA Goddard in New York, but I don't work actually on sea ice, but on glacier ice sheet coupling with climate models. So I changed a bit directions. So I'm going to talk about LKF's intersection angles in sea ice, and a mix of both observation and modeling through the viscous-plastic rheological framework. So first, um, First, I'm going to talk about LKFs, and LKF is our linear kinematic features. And during the talk, I will start with what are LKF and why do we care. Then I will move on to observation of this intersection angle between the LKF and what it means for our modeling efforts. And then a new rheological like formulation for sea ice modeling. So first, like LKFs and the sea ice viscous plastic models. LKFs are really hotspots of processes in sea ice. So it's where we have open water, and that's where thin ice is going to get formed. So and when there's air exchange of heat between ocean and air. That's also where we have a lot of deformation, so through shear and convergence. So it's a place where we get thick ice that get forms. So LKFs are really, they control the thermodynamics and the future deformation of sea ice, because thick ice is going to be strong and thin ice is going to be weak. So it really builds up how the future of deformation is going to happen. In terms of interaction with other things, it's a barrier for movement on ice. So especially when we think about indigenous communities in the northern area of in the Arctic, and it's a path for navigation in water. So an LKF can, when its opening is open water, so ships can go through. So it has this influence on humans and animal activity, and so accurate representation of this LKF is really essential for an accurate and useful sea ice predictions, both for things like navigation and also climate processes. So here's an image from the Sentinel-1 satellite. This is in the East Siberian Sea, and we can see this structure in the ice. So these lines that appear in the radar image, and this is what we call linear kinematic features, because it's lines, but so the place, like I said, where we're going to have movement. So that's why it's kinematic. And we can actually use Sentinel-1 data or other satellite to study how these LKFs are developing and how they are dynamically moving. So for example, here is in latest paper, we we looked at deformation in sea ice to extract where LKFs are. And what you see here is the color scheme is the vorticity of the ice. So in blue, it's going to turn in a negative direction, and in red, it's going to turn in a positive direction. So what we do is we use this information of vorticity to look at the intersection between the LKFs, and we try to figure out if the LKF at the intersection is getting pushed in this axis or this axis. So here it's very clear that using the vorticity that we know that the ice is being pushed from this axis. So it means that what we consider the intersection angle is going to be 43 degree and not the complementary angle of 120, around 120. So we can say that we have a predominance of small intersection angles in sea ice, and this method means that we can actually look at thousands of angles. So it's like an automatic method that we developed to have a better idea of if angles are acute, like here, or obtuse. And one thing that we knew even before this, using this method, is that the models fail to reproduce the distribution of angles that has been observed. By using this technique on two different data sets, so first the RGPS dataset and the Sentinel-1 dataset from Mosaic that we created. So we make the distribution or histogram of our intersection angles, and we showed, like we see that first, it agrees really well between our two datasets, RGPS and Mosaic. And second, that we have really a predominance of small angles between 30 and 60 degrees, and very little like angles that would be around 120 or 140 degrees. And now I will go back into the model. So that was the observation part. And when we want to model sea ice, we need to take into account a lot of processes that we can't represent because they're happening at small scale. And when we look at an LKF at small scale, this is a picture taken by an helicopter pilot on a cruise I had a chance to, an expedition I had a chance to join. We can see how like the dynamical process along the LKF is happening at very small scale. So ice flows interacting, so we have internal stress that's built up. And also a word that I will refer is dilatancy, is the idea that that for the ice to be able to move along the LKF, we often have a dilatancy, so the ice is opening because otherwise you would not be able to move. To represent the dynamics of sea ice that way, we are building, we use what we call a sea ice rheological model. So it's equations to relate the deformation to the stress through what we call a constitutive equation. And in the following, I will talk about the Viscous-Plastic rheological model, which use a yield curve and a flow rule. So what what is this? A yield curve is really a representation of the stresses. So when we reach the yield curve, is that we are going to start deforming. So you can see here on this representation of stresses, sigma 1 is the compressive stress. So positive means tension and negative means compression. And sigma 2 is our shear stress. And so as long as we are we have stresses that are below this blue line, we are deforming very slowly, so plastically. When we reach the blue line, we start to deform plastically, meaning that the stress does not increase anymore, but the deformation increase and it's very fast. And the second thing is what we call the flow rule, is in which direction is the sea ice going to deform? Like, is it going to compress or is it going to shear? And that's why that we talk about this flow rule, which is a representation of how the sea ice is deforming. So if you look at this arrow, you can define it in different ways, and that would be a combination of convergence and shear, or pure shear, or a combination of shear and divergence. Because here, sorry, the epsilon 1 and epsilon 2 represent the axes of deformation. So epsilon 1 is the convergence divergence direction, and sigma 2 is the shear deformation. And then I will talk about normal and non-normal flow rule. So when we define the flow rule, I will not go through the whole mathematical process, but we use a curve that is basically similar to the yield curve, and that's called a plastic potential. And this plastic potential and the flow rule is going to be perpendicular to the plastic potential. But if we take the plastic potential to be the same as the yield curve, we're going to have this arrow that's also perpendicular to the yield curve, and that's what we call a normal flow rule. And the other ones, the orange one here, are the non-normal flow rules. So in like the sea ice models that we use now in, for example, SAIS, like or MIGCM, we use an elliptical yield curve with a normal flow. So you see it would be the gray arrows that are along the yield curve here. And in a previous study, I designed a new elliptical yield curve, but that use a non-normal flow rule, and we use another shape of plastic potential that varies slightly the direction of the flow rule. And using this experiments, I showed that we can change the intersection angle in the model. And that it follows what we call the Archer angle theory. And now I want to show you a small video. And I forgot to show you this one. This is just an example of sea ice deforms in observation. This is not the best example of LKF intersection, but that gives you a bit of an idea of the fracturing that happens in sea ice. So now the stress, like the storm is going to come and going to break a lot of ice. This is the buffer sea. This is at the Canadian archipelago, and this is Alaska. And we see here how the ice get fractured by wind stress. And when we use for example, MIGCM, like a general circulation model with the sea ice dynamical components, we can look at how sea ice is deforming, and you can see how this is the elliptical yield curve with normal flow, and it actually looked quite realistic. We have LKF that are formed. You see really these lines that are created when we have a storm passing by, creating a lot of stresses. But when we look at intersection angles in this simulation, we know that they are too wide compared to what we observed. I'm going to show the data a bit later, but it's more around 90 degrees than around 60. So now just a bit of theory as without going into details, but we have basically three theories that relate our viscous plastic model to intersection angles. What we call the color angle that is based mostly on the yield curve, so it's called like the stress characteristics. There is what we call the Roscoe angle, which is based on the flow rule, so more the strain rate characteristics. And we have there is also some theory that's called the Archer angle that is it's an average of actually both angles, and that could be a possibility from the energy dissipation point of view of CIs. But so just remembering that we have three different theories. And so now what we did, because we had this data set and this distribution of intersection angles, and what we were trying to do is to go from this to a yield curve or a flow rule, like to try to get more information that we could use in viscous plastic models. So we use this distribution to through the process that relates the angle to the shape of the yield curve of the plastic potential. We reconstructed a yield curve, so that would be the orange and blue lines here for both for the two different data sets. And when we look at the shape, we see that it looks more like the shape of a teardrop or the shape of what we call a more Coulomb yield curve, more than the shape of an ellipse. And it also looks quite similar to this violet curve here that's called is a curved diamond that was proposed by Wang in 2007, which uses method similar to ours, but didn't have as much data set data from intersection angle, and didn't use the vorticity to extract in which direction exactly the ice is getting pushed when it breaks. So and so this is our reconstruction, and what we did is we took high resolution model like the one I showed you evolve in the video, and we used the same method, extracted the angles, and we get the PDF or histogram that we can see here in these thick lines, and we try to relate we reconstructed the parts of the yield curve that from these distributions, and we see that the reconstruction is actually quite good. We have a bit of differences that we don't really explain, but we have a good agreement between what the model gives us as deformation as a LKF intersection angle and what even the yield curve that we get when we reconstruct it. There's one other thing is that we looked at the dilatancy along our LKFs, and we see that there is a pretty weak relationship between our intersection angle and the dilatancy. So basically delta is the angle at which the sea ice expands along the LKFs. And if the relationship would be perfect, you would follow this red line, and we are really not close to this. But this could come to the fact that observation have a low temporal resolution of around 3 days for our GPS and around 1 day for Sentinel-1, which is not very high, knowing that LKF fracture happen really fast. So it's possible that we only observe the deformation that's happening after the LKF really started to move. So yeah. So and now I was talking about more Coulomb and teardrop yield curve that fits really well our reconstructed yield curve. And this actually exists in CIX modeling. There was a paper by Chang and Rossrock in 2005 that proposed formulation for a teardrop yield curve and a parabolic lens yield curve with normal flow rule, and a more Coulomb yield curve by Ip in 91 that use a shear only non-normal flow rule. So the flow rule, the CIs along this more Coulomb line is only happening in shear, which could be a problem. I will talk about this. So how do we study in the model, like how do we relate exactly what's happening between the model and between our mathematical model and what happens in the model when we start the simulation? So we did an idealized experiment where we just take a slab of ice, we block it on one side, so like in red, and on the green we push, and we look at which angle are we going to observe in our compression experiment. And then you can also look at, for example, is it going to have a positive dilatancy, so an open lead opening, or is it going to be create a lead, so we have like more ice piling. And this, in the past, we showed that it's really linked to the rheology, so you can really go from this to that. So now studied of our non-elliptical yield curve. First, we studied the teardrop and parabolic lens yield curve. We found that there was some formulation that needed to change because of the formulation of the what we call the constitutive equation was taken from the elliptical yield curve and needed to be adapted to the teardrop, to the precise shape of the teardrop and parabolic lens. So we studied this and changed the formulation and show that you can see here the intersection angle related to one of the parameter of our of this yield curve is the tensor factor KT. And first we can create angles that are in the range that we expect between 30 and 60 degrees. And second, it's like in the elliptical yield curve with a normal flow, we actually follow the theoretical predictions. But this has the problem that as it's a normal flow, it would create a lot of divergence for small angles. And the other problem is that it's the only parameter is this KT factor. So we cannot really tweak our yield curve to what to the CIS properties. So yeah, that while with the more Coulomb yield curve, we would have more control. So then we use this uniaxial compression experiment to study the more Coulomb yield curve. And you see here it's slope parameter mu, so the really the orientation of like this line, how steep it is, and this relation to the intersection angle. And as it is a shear only yield curve, flow rule, sorry, the Roscoe angle prediction is constant. And what we observe is this weird in between intersection angles, and we have a very, very slow numerical convergence compared to other formulation. So we are not really happy about this. And studying this further, we we went into really the details, and like we see that there's really a complex like behavior around the flow rule. So we decided that we wanted to study this further with more different more Coulomb yield curve. So we designed 3 more Coulomb yield curve formulations. First, one that we get inspired by Hibler and Scarson in 2000, which use which has a more Coulomb shape, but with a flow rule that follows an elliptical plastic potential. So we have a flow rule that changes gradually along the more Coulomb slope. And the 2 other one is a more Coulomb that's use the teardrop plastic potential or a parabolic lens plastic potential. and using this, we continue we did our experiments, and we showed that we can create intersection angle in the 30 to 60 degree range. We have faster numerical convergence, but we still have this a bit in between theory. And there is one prediction I haven't shown yet, is this Archer prediction, which is half of Roscoe plus half of Coulomb. And we show that this follows pretty well our Coulomb, our Arthur angle, like the elliptical yield curve with a non-normal flow did. So yeah, this is something we don't really yet understand well, but we repeated the experiment with different value, and we still find that the Archer prediction is better. And so this was for the more Coulomb yield curve with an elliptical plastic potential. And we repeated this with our teardrop and parabolic lens plastic potential, and we get similar result, even though we get also like a slow or bad numerical convergence for this yield curve that have a bit more formulation problems. So if I would summarize all of this, we have observation that we show that small angles prevail in Arctic sea ice. And this is not reproduced in models. When we use the teardrop and parabolic lens yield curve, we can get small intersection angle. We have a normal forward, which is like fast enough for climate models. So like the convergence is not too bad. And we have a more Coulomb yield curve that has a non-normal flow rule formulation, which can be a problem for numerical convergence, but can also create smaller intersection angle. And there's still this relationship between fracture angle and the formulation that we don't really understand. So yeah, so this is a figure by Rampal et al. 2019, where this is the deformation RGPS, and we feel like we are getting closer to someday have a model that looks like this with all these small angles that appear all along. And one thing I wanted to and this is only for the viscous plastic rheological framework, because that's something, this work is really focused on the viscous plastic rheology, which is the one that's used in most climate models today. But the physics are different in other rheological frameworks. So, for example, the Bingham brittle Maxwell model, or the Maxwell astro-brittle model, that really behave like differently. There's more papers on intersection angle related to this physics, these rheological frameworks. As an outlook as well, what's remain like to do is to actually look at the effect of changing rheology in a pan-Arctic simulation. Something that has not been yet done, and it's computationally expensive, especially when the yield curve have a slower numerical convergence. There is the idea that maybe we could use machine learning to extract the yield curve of sea ice in a more like fashion, without a more like automated way that wouldn't need to extract LKFs and then look at intersection angle. And then there is new rheological ideas that come from the field of granular mechanics. For example, like a more Coulomb yield curve that has angles that vary with the flow size of the ice, so what's called a mu of I rheology. Well, that's all like I think interesting directions. And with this, thank you for your attention. And
Great. Thanks very much, Damien. Nice talk. We'll open it up to any questions. If people want to drop them in the chat or just raise their hand or turn on their video, they can go ahead. Yeah, Roger.
Hello, thanks very much. Yeah, and thanks for Damien for the interesting talk. That very first slide you showed, I think it was slide 5, with the big satellite image. Yeah, I
Yeah.
mean, I can imagine structural geologists would get seriously excited about that. The two things I noticed, which I wonder if you could say something about, is that some of the LKFs seem to be offset, perhaps by a later one. Are you seeing successive phases of different directions of ice flow being expressed there? And there seem to
Um,
be almost some curved intersections between the two. It almost looks like somebody's organizing some railway lines.
yes. I think they like the big difference between what I did with my small experiments that are very idealized and this is that here we have a lot of built-in anisotropy, so we have thicker eye, thinner eyes somewhere, and you're absolutely right. I there's a few description of um, how smaller cracks are onsetting like larger ones and how um, our smaller cracks are also created along bigger ones. So you have these wing cracks that get um, created. It's like that's one of like you know I think there
Mm.
is also curves some places because like the storms are kind of round and you get sometimes like depending on the winds like the stress is distributed in some ways that create like curve
Because a lot
factors.
of the algebra you showed us was pretty much 2D. I mean, I wrote down sigma 3 question mark. So there's obviously the chance for some up and down movements, some thickening at the same time.
Yeah, we make the assumption that it's all vertically integrated stress because we look at sea ice around like thousands of kilometers and um and the thickness of the ice is what maximum 40 meters maybe. It's very difficult to model like the 3D. That's why we have this ridging idea in the compression zone of the yield curve. So it represents a bit like thickening of the ice. And I agree. That would be great to be able to do it to do it in 3D, but we are not there yet, unfortunately.
Smashing. Thanks very much. That was a really enjoyable talk. Thank you.
Thanks to you.
Alec.
Hi, thanks. That was a really nice talk. Maybe a bit of a random question, but I was wondering if you or like your colleagues ever look at the kind of LKFs and intersection angles along coastlines where you have more of a fixed boundary, or does it tend to be kind of within the ice pack, away from coastlines, or could you learn something from looking at it where one side of your
Mm,
stress or shear is fixed?
it's possible. I've done some experiments when I was exploring. I didn't I didn't continue this, but I wonder if like it's just it gets more complicated. The eyeglass experiment has the really the
Hmm.
advantage is that it's very simple. We know what the stresses are going to be.
Hmm.
Um, and and we know actually that our model achieve a good numerical convergence when things are pretty symmetrical. But there's a few papers that looked into this. I think of Allingson 88, where like but I think it's a different theory of failure. I'm not sure
Hmm.
how this all yeah, we try to avoid actually the the coastlines because we know it's going to make it more complicated.
Okay.
For example, in the observations with RGPS and Mosaic. But Mosaic was not close to the coast, but for RGPS we just removed the coastlines, like around the coastline, because it's too complex.
Cool. Yeah, thanks.
Yeah, thank you for your question.
I had a quick question, and I'm pretty negligent in this in this field, but can you go back to your vorticity slide where you define the intersection angle? I'm just curious again if you could just recap how you define this at 43 degrees versus the inverse of 140 degrees, because I noticed in your distributions it goes from 0 to 180. So I'm just wondering how you differentiate between the 40-degree angle here, which you're showing, versus measuring the 140-degree angle on the other side of that fracture or that LKF.
Because we have the vorticity, especially the sign of the vorticity for both LKFs, we can say that, like, the ice, like that's shown in blue here, is turning in this direction. The ice that's in red is turning in this direction. So we know. Ooh, I have a very sensitive mouse wheel. We know that this piece of ice is moving this direction compared to this and this piece of ice. So we know that basically it's like we are pushing from the top or the bottom, and it's get expanded on the side.
Okay, I see.
And like if this LKF would be red and this one would be blue, we knew that it would be pushing on this side, because the LKF the rotation would be like inverse, like this, and we would say it's a 140 degree angle.
Okay.
Yeah, that's. I should have. I have a figure for this. I should have like put it on it. But
Is there anyone else?
Yeah, I was maybe just going to ask another quick question while others are maybe waiting. You kind of mentioned like next steps, and it seems like you may be kind of implying that there's enough IGPS data supplemented maybe with the Mosaic data to be able to kind of do a lot of model improvement work. What do you see as the kind of observational gaps or exciting future observations potentially that could help with this work?
So I think actually I don't think we have enough observation. I mean, we have only a few years for RGPS, and Sentinel-1, there is a gap because now we only have one satellite working, if I'm not mistaken.
Right. Yeah.
But there is a new RadarSat constellation mission that has been up for a few years, and there is a low resolution dataset for sea ice motion that has been out by Environment Canada. And I've been working to get a higher resolution deformation dataset, so that would be like RGPS. I think it's just, I think we, like, by using, what I meant is that by using observations to constrain the model, we are getting closer to like knowing what's how to model sea ice correctly. I'm not 100% sure that this teardrop yield curve and Markov yield curve will work in the viscous plastic model. Like that's why I say it's like we still need to see how it works on the large scale, because my experiments are really on idealized models to understand the physics behind it, but how it works in the full like Arctic wide model is another thing.
Cool.
I don't know if
Yeah,
I
that makes
answered your
sense.
question.
Yeah, no, you did. You did. Yeah. Thank you.
Great. I don't see any other hands coming up, so I think we'll call it there. Thanks everyone for taking part, and thanks Damien for a great talk. I really, really enjoyed that. We are back to the seminar series taking place every week. We're scheduling sea ice talks, continuing forward. So if anyone from your group or yourself would like to volunteer to give a talk, please reach out and let us know. We'll also share, I think, pretty soon in CryoList, and I hinted towards it in my posting, but we're going to begin shifting one seminar a month to a later time in the day so that we can get better overlap with people in Australia and New Zealand and Asia. And so I've been working with some people in Korea and Japan to try to recruit some speakers from that side of the world that will now be more available for them. In the past, it's been tricky with the time change, with time zones for them to watch these live. So we're trying to accommodate them. It'll become the middle of the night for Europeans and sort of evening for those of us in North America. But we'll be sending out some more information about that. So we're trying to diversify our talks a little bit and accommodate other groups that haven't been able to take part in the seminar series. But yeah, thanks for everyone for joining, and I look forward to seeing you next week.
Thanks a lot.
Yeah, thanks so much, Damien. That was great.
Yeah, thanks. That was a nice talk. Appreciate it.
Thanks to you all. Bye.